Hi, welcome to a lecture on antenna temperature. Antenna temperature is a way to characterize the external noise that's received through an antenna, and it's an important parameter for calculating the sensitivity of a receive system. So the scenario in which antenna temperature emerges as a concept is the one shown here. We'll start with a lossless antenna. It's important that the antenna be lossless for this initial analysis because the loss in an antenna would also generate noise, and that would be confused with the external noise that we're trying to characterize here. So initially, at least for the purposes of this lecture, we're going to assume the antenna is lossless so that all the noise comes from outside the antenna. Here is the external noise incident on the antenna. The impedance of the antenna is Z sub A, and we have to somehow observe this noise. So we have a measurement receiver. The input impedance of the measurement receiver is Z sub in. And again, for the purposes of this analysis, we're going to assume that it's conjugate matched so that the maximum power is transferred from the antenna to the measurement receiver. What we're ultimately going to measure here is the power density, that is the power spectral density, which is delivered to the receiver. We're going to give that the symbol S, and it has units of watts per hertz. So, under these conditions, we can define an antenna temperature, T sub A, which is defined as indicated here, S divided by K, where K is Boltzmann's constant. That's little k. Big K is the units of temperature, Kelvin, and the reason we call this antenna temperature is simply because it has units of temperature. So antenna temperature is just another way of talking about the power which gets delivered to a conjugate matched receiver which has originated externally from the system. Now we need to make a couple notes here. One is this definition only makes sense if the signal is actually noise-like. That is, it has no discernible structure in time or frequency. If the signal looks like a sinusoidal signal, or if it looks like a modulated signal, that's hard to characterize as noise, except for certain circumstances which are outside the scope of this lecture at the moment. Also, we could express this as a noise figure, and this is sometimes done. The conversion between an equivalent temperature and a noise figure is discussed in another lecture. So, in principle, if you chose a reference temperature, T sub naught, you could use that to transform T sub A into an antenna noise figure. Now this is sometimes done. I don't recommend it. It's not very common and is generally confusing because it becomes commingled with your choice of T sub naught. When these conditions are satisfied, the equivalent circuit becomes the one shown here, where on the left we have an equivalent circuit for the antenna as a Thevenin equivalent circuit source. And on the right, we have an equivalent circuit for the receiver, which is simply a impedance as a load. Now on the left, we have the radiation resistance of the antenna. Remember, the impedance of an antenna is radiation resistance plus J times the antenna's reactance. So we have the radiation resistance here. We have the reactance here, and then we interpret the antenna temperature as being the physical temperature of a resistor, which has the value equal to the radiation resistance. So in this model, antenna temperature works like a physical temperature. But don't confuse this with the real situation, which is simply that the radiation resistance looks like a resistor, and the physical temperature of that resistor is T sub A. And you might ask where the source is. Well, the source is the noise, the physical temperature. So as discussed in another lecture, any resistor having a physical temperature generates noise, thermal noise, associated with that temperature. So here, thermal noise is standing in for the external noise that T sub A represents. Now, we're considering lossless antennas here, but you could fairly ask, what if the antenna has loss? And I'll briefly address that and then forget it for the rest of the lecture. The idea is that if the antenna has loss, then the impedance of the antenna is going to be radiation resistance plus the reactance of that antenna, plus a loss resistance, which is the physical resistance in the antenna. So we would end up adding an extra resistor, which has value, resistance, R loss, at a physical temperature equal to the physical temperature of the resistor. So the second resistor in series would have value R loss, and it would be at a temperature equal to the physical temperature of the antenna. So you'd get more noise, but this isn't part of the definition of T sub A, which is why I'm neglecting it for the moment. Remember, T sub A is a characterization of external noise and is not intended to capture the noise due to the internal resistance within the antenna. So, you might ask, what values do we expect to see for antenna temperature? So let me give you two scenarios which will kind of give you a preview of the possibilities. In the first scenario, we put a lossless antenna. It doesn't matter what kind of antenna, any lossless antenna, inside a chamber. The chamber has walls with black body material, and the physical temperature of those walls is indicated as Tphys. In this case, we know that there are no reflections within the chamber. That's what it means to be a black body. But the walls will radiate because they have heat. And whenever you have heat, you have vibrating electrons. And whenever you have accelerating electrons, you have radiation. That thermal noise is what the antenna will measure as the antenna temperature. And in this case, T sub A, the antenna temperature, equals the physical temperature of the walls. The second scenario, to preview possible values of T sub A, goes like this. We have a lossless dipole. In this case, I want a dipole because I want something which has a pattern which is symmetric vertically. So the pattern of this dipole is a dumbbell shape which has equal directivity in the up direction and the down direction. So I have a lossless dipole connected to the measurement receiver. This dipole is suspended in the air, and below the dipole we have Earth at 280 K physical. So 280 K is a typical temperature for the ground. Above the antenna, we have the night sky, and I want to say the night sky because I don't want the sun to confuse the issue here. Well, you might ask, what antenna temperature do we measure in this case? Well, it depends. It turns out that at frequencies around 10 gigahertz or so, the antenna temperature is going to be a little bit less than 280 K. For frequencies around 100 megahertz or so, turns out the antenna temperature is going to be on the order of 1000 K. So what the heck is going on here? This is what we'll talk about next in this lecture. The reason I want to show this example first is because there is a common notion that shows up a lot, which is that the antenna temperature is typically 290 K, which incidentally is equal to the IEEE reference temperature for noise figure. As you can see from this example, 290 K is pretty arbitrary. It's in the range, but again, the range could be less than 280 K all the way up to thousands of Kelvin, or more, depending on the frequency range. So we can dismiss the commonly asserted notion that T sub A is typically 290 K. That is ridiculous unless you know in your particular scenario that it actually is close to that value. To facilitate a proper calculation of the antenna temperature, what we do is first define a brightness temperature. We'll define the brightness temperature as the antenna temperature measured by a particular antenna, and that is one that has a beam with a normalized pattern, which is a delta function, a sampling function in angle. Now, we've used this idea of sampling functions before, and it's playing the same role here. In this case, the sampling function is defined to be 0 in any direction other than 0 theta 0 phi. And when you integrate over a sphere, including the antenna, then the value is 1. So this lets us get around the problem of saying what the value is at theta equals 0 and theta equals phi. So what we have defined here is a beam with a 0 beam width. In other words, it is the narrowest possible beam. Now, I'm not saying we can have such a beam, but it is a useful concept for defining the relationship between antenna temperature and brightness temperature. So what we say is that if we take the brightness temperature, which is a description of the noise now incident on the antenna as a function of theta and phi, we multiply by the directivity, which is going to say something about how that power is captured, and then we integrate over a sphere. That's going to be theta 0 to pi, phi 0 to 2 pi, times a unit element of solid angle, which is sine theta d theta d phi. Well, what we know we're going to get for this particular antenna that we've defined that has this magically narrow beam is the antenna temperature times the solid angle of a sphere, which is 4 pi steradians. So we can divide through by 4 pi steradians, and we get that the antenna temperature is equal to 1 over 4 pi, which comes from here, times this integration over a sphere of the product of the brightness, temperature, and the directivity. So what's happening here is brightness temperature is describing the environment. In other words, how much noise is coming from a particular direction. Directivity is talking about how our antenna of interest, not the test antenna here, but the antenna of interest is receiving that incident power. We integrate over a sphere and then we divide by 4 pi. That gives us the antenna temperature. So given brightness temperature, we can now calculate antenna temperature. So here are 2 examples. In the first example, we're back to a chamber with black body walls at physical temperature T-phys. In this case, we'll have a lossless antenna connected to the measurement receiver, which has magically isotropic response. Now, again, as we've probably addressed before, there really is no such thing as an isotropic antenna, but the concept of an isotropic antenna is useful, and so we're going to use it here to demonstrate something. So an isotropic antenna would have uniform directivity in all directions. So let's see what we get for this antenna. Well, from the problem statement, the brightness temperature as a function of angle is always T-phys. Because no matter which direction I look in with a super narrow beam, that super narrow beam will always see a brightness temperature equal to the physical temperature. So as I point a super narrow beam around, I always see the physical temperature. And because the antenna is isotropic, the directivity is just 1. So now we just use the expression. The antenna temperature, 1 over 4 pi, integrate over a sphere, brightness temperature times directivity. The brightness temperature is the physical temperature. The directivity is just 1. And now what I'll do is I'll pull out the physical temperature since it's a constant with respect to the integration. And what's left is this expression, which is the solid angle of a sphere. If I integrate over a sphere with an integrand equal to 1, I get the solid angle of a sphere. And if I divide that by 4 pi, then I end up with 1. So the answer is simply that the antenna temperature is equal to the physical temperature, which is good because that's what we said we should get at the beginning of the lecture. So we can see this expression works in at least that case. Example number 2, slightly more realistic problem. In this problem, we have earth ground. We have an antenna close to the ground, which in this case is high directivity, has a narrow beam, and the beam's pointing up, so it's pointing towards the sky. And in this case, the sky has a uniform brightness temperature of 10 Kelvin, which could represent the sky at frequencies of gigahertz, tens of gigahertz, so on. In the lower half space, which includes the ground, the brightness temperature is going to be roughly 280 Kelvin. Again, I say roughly because it will change for a number of reasons that we can talk about a little bit later in this lecture. But we'll say here that's about 280 Kelvin. So a perfectly narrow beam, not the one we're using, but perfectly narrow beam, sees 10 K whenever it points anywhere above the sky, and sees about 280 K whenever it points below the sky. So what happens in this case? Well, in this case, T sub A is slightly greater than 10 K. Why? Well, if we're a perfectly narrow beam pointing up, we'd see exactly 10 K. It's not perfectly narrow. What happens is some part of the pattern is extending below the horizon and picking up power from the ground. So we don't get 10 K after the integration, we get something greater than 10 K. Similarly, if the beam were to point straight downward, straight into the ground, then if it were perfectly directive, if it had 0 beam width, we would measure about 280 Kelvin. But for this realistic antenna, if we point straight down, the side lobes and the back lobes will be partially above the ground, so we'll see an antenna temperature which is slightly less than 280 K. So we see that the antenna temperature is an integration over the full sphere, and we see how antenna temperatures can be more or less than the brightness temperature of the thing that the antenna points at. So now the question would seem to be, what are typical values of brightness temperature? I've given you some representative values, but how do you figure out what actual values should be? Well, first, let me say that brightness temperature, of course, depends on the source of the noise that is creating this brightness temperature. And I can break this up into 2 broad categories. Natural noise, noise which occurs in the natural environment, or anthropogenic noise, which is man-made noise, noise which is generated as a result of human activity. So, natural noise. Natural noise, some categories include here terrain, as we've already alluded to, which will have brightness temperature on the order of the physical temperature, but the exact value depends not just on the physical temperature, but also on the properties of the materials that comprise the terrain, and also the orientation of the terrain. Polarization plays a role in all this. Now that's relatively complicated stuff, but the headline here is that terrain has a brightness temperature on the order of the physical temperature, and it's hard to do better than an order of magnitude guess without taking into account the materials and the orientation. Another source of natural noise is the atmosphere itself. The atmosphere is comprised of many things, but a big chunk of that is water vapor, water in gaseous form, and that will account for somewhere between 1 and 300 Kelvin at frequencies UHF and above. Now this also depends on the path relative to the zenith, so you get different values for this contribution depending on whether you look straight up or whether you look close to the horizon. Another source of natural radio noise, which can be represented as a brightness temperature, is the moon. The moon is about 200 Kelvin or so. But its angular extent is pretty small. If you consider how big the moon is in the sky, it is pretty tiny. It's about the size of your thumbnail held at arm's length. So, a tiny fraction of the sky. So the contribution to the antenna temperature is small, as long as you don't point directly at it with a very narrow beam. Now let me elaborate on that. Here's the moon. The rest of the sky is at some temperature T sub sky. If I point a highly directive antenna straight at the moon and the beam width is less than the extent of the moon, then I will measure the brightness temperature of the moon as the antenna temperature. That'll be about 200 K. If I take that same beam and point it away, I'm going to see primarily sky, and only the side lobes will intersect the moon and will make relatively little contribution if this antenna is highly directive. So in that case, I will observe that the antenna temperature is roughly equal to the sky temperature and a little bit different based on the contribution of the moon. Now if I have a low directivity antenna, in that case perhaps the moon occupies a position somewhere within a half power beam width or so. But in this case, the antenna temperature will still be pretty close to that of the sky temperature because the moon occupies a relatively small angular region of the sky. So only in this case do I see that the moon makes a significant difference in the antenna temperature. Now those are all what we call thermal noise mechanisms. In other words, the noise that we're accounting for there is due to temperature. But there are also non-thermal mechanisms that are natural. And these include the quiet sun, which can contribute a brightness temperature between 1,000 Kelvin and 1,000,000 Kelvin, depending on the state of the sun at any given time. And this is the quiet sun. When the sun is active, then this can be spectacularly greater. But the quiescent quiet sun, somewhere between 1,000 and 1,000,000 Kelvin or so. And this is often important despite the small angular extent of the sun, because it is so bright. So even though the sun takes up a relatively small portion of the sky, so the condition I described for the moon applies, the sun is so much brighter than the moon that it can still sometimes make a significant contribution. And you need a lot of directivity typically to make this contribution truly negligible. So the quiet sun may or may not be an issue, and if you really need it to not be an issue, you better have a lot of directivity. Another non-thermal mechanism is the galactic synchrotron radiation background. The story is this: the galaxy is full of electrons which are being accelerated by various astrophysical processes. Whenever you have accelerating electrons, you have radio emission, and that radio emission is readily detectable on Earth. In fact, it is the dominant noise contribution to antenna temperature at VHF and below in many cases. The contribution from the galactic synchrotron background can be a brightness temperature which is greater than or much, much greater than 10 to the third kelvins. So we're talking about brightness temperatures comparable to that of the quiet sun, but much more difficult to avoid because the galaxy occupies a huge chunk of the sky and not just a small circle like the sun does. So the entire sky is bright and lumpy at frequencies VHF and below. You see brightness temperature on the order of thousands of kelvins, below 100 megahertz. The good news, though, is that it fades dramatically with increasing frequency. In fact, these numbers go down in proportion to approximately frequency to 2.5. So by the time you get up to gigahertz frequencies, this galactic background is typically insignificant. And then we have the cosmic microwave background, which is another astrophysical background. That exists everywhere you look in the sky, and it's 3 Kelvin. So even if you are somehow magically able to avoid the galaxy, the sun, the moon, all the other things I've addressed above, you still see a background, and that background is at 3 Kelvin brightness temperature. So if you are sensitive to signals on this order, then the cosmic microwave background is an important source of noise that shows up in the antenna temperature. Then we have anthropogenic sources of noise, in other words, noise due to human activity. This is the combined roar of zillions of devices all producing RF pulses. So electronics that have clock signals in them, engines which have spark plugs in them, sparking away, all producing all these pulses. And since any receiver has a finite bandwidth, they see these pulses as noise. All these pulses appear to be a noise phenomenon because the bandwidth of any practical receiver is limited. So a sufficiently narrow pulse with a sufficiently narrow bandwidth is indistinguishable from noise. You need a broad bandwidth to see some of these pulses as actually being pulses. So even though the source mechanism may not be noise-like in the sense I said previously, which is void of structure in the frequency and time domains, in fact, it appears to be devoid of structure in the frequency and time domains because the bandwidth is limited, smears everything out. So anthropogenic noise, of course, arrives primarily from the horizon because that's where the people and their devices are at. This is important at UHF and below for sure. As you get to higher frequencies, you see it roll off with a roughly frequency squared dependence. So as frequency goes up, this noise temperature contribution from all this human activity tends to go down. Here is one plot that kind of shows what's happening at frequencies where this is relatively well understood, which is below 300 megahertz or so. So below 300 megahertz, you see a galactic synchrotron background that goes down like this. And then quiet rural is comparable to galactic. And then there's different curves here indicating increased levels of noise as you'd expect as the population density goes up. I have to warn you, this information is greater than 40 years old. There's really been no significant work done on these noise levels in recent decades. And really, there's no consensus now on what the current situation or the trends in the situation are. This is quite remarkable if you think about it, but nevertheless, it's true. So if you think you are limited by anthropogenic noise, and you may well be, it's really necessary to do measurements or to find a reference which is specific to your application. And it's quite reasonable to expect that what you see will be different from the noise models which are currently available, simply because those noise models are quite ancient at this point. This concludes this lecture on antenna temperature.